Okay, so today I'm going to cover some advanced topics in blockchain. And these are things that if you really like this stuff, that there are some research papers I can point you to. I can point you to some systems that are being developed that you might come across eventually if you stay in this area. One of the things I want to talk about first are block times versus block sizes and what's being done to adapt both of these to applications that people really want to run on the blockchain. And so if you recall, when we were talking about Bitcoin, it has this parameter called block size, and it's set right now to be like 2 megabytes. And because it's set to 2 megabytes, the number of transactions you can actually jam in there is limited, and you only get a block every 10 minutes. And so as a result, there is this tension where people want to treat Bitcoin as a currency, where you're able to do these transactions like in real time and a whole bunch of them. And the problem is that it doesn't have the transactional throughput to allow that. Instead, it's more like trading stock, where rather than doing like for your credit card, rather than doing like multiple transactions, perhaps in a day, you might do one transaction a week. And so right now, Bitcoin is configured to do more like stock trading. It's more of an investment and less of a currency. But you have these factions. A bunch of people want it to be a currency, and the other folks want it to remain an investment. Okay, so it's basically 7 transactions per second, and so this is more like a stock and less like credit card or cash. So within Bitcoin, in 2017, there was this thing called the segregated witness upgrade, and it was actually a patch to fix this bug in the Bitcoin code for basically validating transactions. And a side effect was that it effectively doubled the block size. And the people running Bitcoin were like, that's good enough for increasing the block size. We're going to leave it at that. Well, there was another subsection of Bitcoin proponents who said, that's not good enough. We're going to fork the blockchain. And that's what happened. So Bitcoin Cash was hard forked soon after this upgrade, and they adopted a much larger block size. So it's 8 megabytes. And then eventually Bitcoin Cash forked again, because even those people couldn't agree on the block size. And so now you have this Bitcoin ABC, which has 32 megabyte cap size, and then Bitcoin SV, 128 megabyte size. And this is where you're starting to see like a whole bunch of different versions of this, yeah. Yeah, that was the, and we'll get to the block times in the next slide, but if you recall, this double spending problem. If I were to add 2 blocks very quickly, I could double spend a token. So what you want to do is you want to add a block and then have everybody agree that that block is part of the ledger so it can update the balances of everybody who's spending. If I submit 2 simultaneous blocks, I can try and double spend a coin. And so the idea was that if I delay the times between blocks, the time between minting a new block versus propagating the blocks to everybody, it has to be really large. So I want everybody to get the new block quickly, and then I want the next block to be done well after that, so that everybody has the complete transaction state in order to validate the next block. So if you shrink the block time, and we'll see this later, you might get into these issues of double spending. And so Bitcoin, the model of Bitcoin was 10 minutes between blocks, and then a certain number of transactions per block. So not only did they want to avoid double spending, but they also wanted the hardware used to store the blockchain to be modest. So you could store the blockchain on a Raspberry Pi. So this is why these are design choices for Bitcoin, but because of those design choices, you don't necessarily have transaction throughput to do like credit card style processing. You get 7 transactions per second, which ain't good enough for a lot of people. Oh, that's, so Ethereum, we'll talk about this in the next slide. So Bitcoin, we haven't really been doing any transactions on Bitcoin, but if we were, you'd be waiting 10 minutes rather than 30 seconds or a minute to see your transactions. So Bitcoin is definitely this every 10 minutes you get a new block. So in order to wait for a confirmation on a transaction in Bitcoin, not only are you waiting at least 10 minutes, but typically, because you want to avoid, being sort of orphaned, you want to wait multiple transactions after that. So typically, I think I showed that chart where it's like if you got like $5,000 transaction, you want to actually wait maybe half a dozen blocks to be committed before you consider that as being committed to the blockchain. So that's like a 1 hour latency before your transaction can be sort of relied upon, is the idea. Ethereum, the block time on Ethereum is, it's under a minute. And so that's the difference. And we'll talk about why Ethereum went to this, because Ethereum's going to have this issue now where you could get things that are divergent in their states. So are there any other questions about block size? So this is relatively straightforward, but because the people managing the blockchain couldn't agree upon the direction that Bitcoin wanted, that they wanted Bitcoin to go, they said, we're going to create different Bitcoins. And so this is how you have multiple networks. I mean, that was the main driver for some of this stuff, yeah.
Why is the block size such a limiting factor?
I think it's, so the folks who really want this to be decentralized wanted anybody with a piece of hardware to be able to participate. And that gives you security. So if we have the blockchain and if all of us could run a full node, and all of us could with our Google Cloud credits, then that is actually a powerful way that can't be subverted by maybe a centralized authority. And they can't modify the thing because then they have to basically get agreement from everybody to change that.
That would be a lower limit, but why do you need a huge size block?
For just throughput. Like, yeah, if you really want, you say, I don't care about having it be distributed everywhere. I would rather sacrifice that security in order to make it usable. Because right now there's proponents who are like, yeah, Bitcoin, people aren't going to use Bitcoin because it's, why do I have to wait an hour for me to get a validation of my transaction? So yeah, there's these competing, and anytime you have a bunch of people trying to agree on something, you'll end up getting stuff like this happening. So, okay. So larger block, and we just talked about these issues. Larger block sizes means that the amount of hardware that you need to run a full node goes way up. But it gives you decreased transaction time, decreased transaction cost, because there's not as much competition to get into a block. That way your transaction fees can be lower because there's more supply for the demand for transactions that are out there. But it also increases propagation time. If you're going to transfer an 8 megabyte block, it just takes a little longer than the 2 megabyte block that you had before. Or in this case, 128 megabytes. Like if every one of these is 128 megabytes, then propagating that to all the full nodes will take a little longer. Okay, the other thing to think about is block time. And so, like when you compare Ethereum to Bitcoin, Ethereum has a much shorter block time. You're getting these new blocks every 30 seconds or so. And so, anytime you decrease block time, you're basically improving the transaction throughput linearly. So the impact is that the consensus algorithm now has to do more work. It's much harder to get consensus when the state is constantly changing. Especially in the presence of network delay and network faults. And so because of this, you'll see that the orphan rate, which is the rate of the amount of work that eventually gets orphaned off because of, it's on an invalid chain, the amount of wasted work on that is going to increase. And so if you are mining blocks that eventually get orphaned, you'll see that the actual computational resources wasted will go up as well. So that's another parameter. And the example that shows this is from this link here. If you click on it, they show this figure. I have 3 nodes here, and they're each trying to update a blockchain, the blockchain state. And say the middle node mines 2059, propagates it out. The top node mines 2060, propagates it out. and the bottom node 2061. So they're all mining blocks, distributing state. And so the idea here is, what if we made the block time much smaller? What might happen in this case? So here's a picture of doing this. So the arrows mean, the arrows going from left to right means that all the miners are continually mining on whatever the next block is. And as we saw before, the oval is that they mined a block successfully. And then these arrows, these vertical-ish arrows, mean that they're trying to propagate the state of the next block to the other two miners. So here in 2059, you see that this thing gets mined and immediately broadcast to the other two miners, and the other two miners, they want to immediately switch to that block and mine the next block, because no miner wants to mine a block that eventually gets stale. So they have the incentive to switch over to start mining from 2059 almost immediately. And so this is the way you want things to work, where as soon as a block is mined, it gets propagated, everyone adopts the new state, and then starts mining from there. And in this case, there's not as much wasted work, as we'll see. Okay. The problem with a block time that is too short is that here you have, for example, 2059 is mined and broadcast, 2060 is mined, and before it finishes broadcasting, another version of 2060 is also mined and broadcast. And then when this thing gets propagated, you have a conflict here. You have two valid 2060 blocks, and now you have to undo some work here, because this person was mining one 2060 block and then got another one, and so has to figure out which block to mine. And so this is the situation that happens when your block times are too small. You'll get a lot of people mining different state than the state that was eventually accepted as valid. So you could, if you were one of the unlucky people, so say eventually this thing won out, if you were one of the unlucky miners that got this block first, you would be thinking that you're mining the actual valid blockchain, when in fact a bunch of people are mining some other subchain. And that's the bifurcation that causes an issue with a short block time. Okay. Does that answer your question? Okay. Okay, so miners working on different versions of 2060 create wasted work, and with no added stability to the blockchain. Typically, you want the work consumed to make the blockchain more stable. In this case, it's causing a split, so it's actually not doing that. And so the shorter your block time is, the more wasted work that you do. And so this is why mining pools are very cognizant about having a really fast network connection. You want to know as soon as possible so you can start mining the next block in the blockchain as quickly as you can. Okay? Okay. So the way Ethereum addressed this, the Ethereum block time is extremely small. And the way they did this was to change the incentive structure of mining. And so their idea was this greedy, heaviest observed subtree in a block will determine your reward. And so this is, the goal is to eventually incentivize miners to coalesce on a shared tree. And so the way this works is anybody who mines a block, what the algorithm does is it takes all the common subtrees out of the mined blocks, and that's the one that's committed to the blockchain. And then if you have mined a block that doesn't necessarily have all of the transactions included, you'll get some partial credit for having a subtree that eventually made it into the blockchain. And that's the way they do it. They figure out what has been shared amongst all the miners as being valid, and then we'll partially give out credit for those who have that in their mined block, and then move on to the next one. So that's their algorithm for avoiding this. They call these blocks that have these parts of the subtree that don't overlap, they call these things uncles. And the idea is to minimize the amount of uncles in the network and to make sure that people have the incentive to avoid generating more uncles. So as soon as you see what has been accepted as the subtree, the valid subtree, you're immediately going to adopt that and move on. Okay, so block times in practice, Bitcoin's at 10 minutes. And one of the things that they've been talking about is changing this block time because it takes about 12 seconds to propagate a block to 95% of the nodes. And so realistically, an order of magnitude on top of this would be maybe a 2-minute block time rather than a 10-minute one. So they've talked about that. And then in Ethereum, it's 10 to 20 seconds due to the fact that they're more aggressive with their mining scheme. Okay, the next thing I want to talk about also deals with scalability, and this is sharding and side chains. So the first thing that you'll notice on Ethereum is that resources are expensive on it. And the reason why this is the case is because full nodes are basically performing the entire computation of everyone's transactions, as well as storing all of the contract state across all the full nodes. And so the reason why you have this gas limit is to prevent someone from doing a denial of service attack on the network itself. So you're forcing people to pay in order to get these transactions through. But still, the way they've configured it, Ethereum is open to denial of service attacks. Like someone with a reasonable amount of ether could actually just clog the entire network and bring it down for, however long they wanted to keep that thing down. And so then the question is the cost of launching this denial of service attack, does that actually outweigh the damage that can be done to people who have built their business on Ethereum? Because if it's much cheaper to launch the attack versus the amount people can lose, you got extortion right there. You're just like, hey, you got a nice Ethereum smart contract there. It'd be a shame if something would happen to it. You can pay me, a certain amount of money, and I'll make sure I won't DOS the network. And so, Black Friday. I don't know if you saw this. Costco, the Costco site went down, and they were saying that they lost like $11 million. They estimated $11 million of sales went down the drain. The same thing could happen if you have a business that requires you to use the Ethereum an Ethereum smart contract, and then on the time when you need it the most, somebody can just spend a modest amount of ether and DOS you. You have a problem. Okay, so that's what this is about. Okay, another issue is that you have a single blockchain for all of the distributed applications to share. And this is actually implementing a total order on all of the events in all of the contracts. And so for dApps that are actually independent of each other, you don't need a total ordering between the events between those two contracts. You only need a total ordering on the events within a single contract. So why is this necessary is the question. And so this is an issue with CryptoKitties. This is a fun and games app that basically, when it got popular, basically wiped out all the other apps that were there because because people were using Ethereum for this, and then any of these other smart contracts were suffering as a result. And so you don't want your business to be reliant on something like this bringing you down. And these are issues that people are like, yeah, we can't use Ethereum now. There's just too much risk involved in getting something running on Ethereum. Okay, so people have been talking about, and if you follow Ethereum, the sort of the efforts in Ethereum to fix these issues, one of the things that they've talked about is sharding. And the idea here is to divide the network into subnetworks, and then each shard will store a fraction of the blockchain. And then you would basically, within this shard, you would create some state independently, and then eventually synchronize it to a full node at the top, is the idea of a shard. And so the idea of doing this as a hierarchy has come up, and this is what Ethereum 2.0 is looking to do. Another thing to do is very similar is to use a state channel. We talked about Bitcoin, these channels, basically the Lightning Network payment channel, where it's more like going to a bar, opening up a tab, doing a whole bunch of transactions, and then the closing of your tab is the only transaction that gets committed to the Bitcoin network. The same idea could be applied to smart contract execution, right? So you can have Alice and Bob check out a state for contract X. Say, hey, you know, we want to interact with contract X. Contract X has, our interaction on contract X is quite complex. We're going to have like, you know, maybe hundreds of transactions in this thing. And so what I'll ask for the blockchain is to get the entire state of contract X, and then Alice and Bob will interact on that contract through some other channel, mediated by perhaps a trusted third party. I will change the state of contract X, and at the very end, that final state of contract X is what I'll commit to the blockchain. And then the main network has only these two transactions where hundreds of states could have been changed in the meantime. Okay, another interesting area is formal verification. We touched upon this briefly already. So you want to be able to ensure the correctness of the Ethereum, the virtual machine itself, and people are applying this theorem prover, Isabelle, to verify the different components of the EVM. Once the underlying EVM is shown to be provably correct, the other thing to do is to apply formal methods on the smart contract itself. How can you prove that a smart contract doesn't have bad states? And so domain-specific languages, like this Y3 programming language, have been developed to allow someone to be able to apply formal methods onto smart contracts to ensure that they don't have problems with them. And then another approach that people are using is to integrate contract testing in the IDE itself. And this is similar to in DevSecOps, where you're trying to push the security audits towards the developers. That would be what this is doing. So in your IDE for smart contracts, and this is done with Truffle, there should be some automated testing going on so that before I even deploy a smart contract, I have some warnings. And this remix has a little bit of this. When you compile a remix contract, you'll see some of the warnings if you choose to click on the tab, which I choose to click on the tab just to see what I'm doing wrong. You'll see that, hey, you're using self-destruct. This is a potential vector of compromise. So these sorts of things are being done on smart contracts themselves. Another interesting area is decoupling the state machine and consensus. So what does this mean? So right now, the Ethereum virtual machine and Solidity, they conjoin the state in the contract with the replication of that state across the nodes. The programming language and the virtual machine are deeply tied into the replication protocol. So the idea of this thing, this Tendermint thing, is that why can't we decouple those two things? A state machine is a state machine, and why can't we just use the blockchain as a replication service, is the idea. So why can't I write my dApp in Java and then have the blockchain replicate the JVM in a shared state across all the participants? So I don't need, so the idea is that why would I need a specialized programming language, Solidity, that, you know, and tie it to the Ethereum virtual machine so that the only thing that the EVM can do is run a specific kind of code. So this is what Tendermint does. It separates the state management. It separates the programming language and the virtual machine that it runs on from the replication and the consensus of that virtual machine. So then this allows you to write smart contracts in any language that you prefer, right? Not just Solidity, which we all love, I guess, in this class. Okay, another thing that is being looked at is thwarting miner centralization, and we actually had covered this quite well in the previous slide. So one of the issues is that 80 to 90% of all mining hardware in Bitcoin is actually produced from a single factory in China. So all of the ASIC hardware is basically produced by these folks, and there are some alternatives. So if you want to avoid having all of your sort of the security parts of your blockchain reliant upon one vendor, There are things that you can do. One alternative to having everything done by ASIC is this area of memory-bound puzzles. So there are many computational puzzles that are out there, and some of them maybe in your algorithms class you might have come across. One interesting area is this memory-bound puzzle, and you'll see that there's a lot of cryptocurrencies that have done different proof of work for doing their mining, and some of them will do memory-bound. In fact, I think Monero is doing a memory-bound puzzle, which is why you can hijack a regular CPU and start mining. In fact, all of you could actually participate on Monero mining, and this is why adversaries are going after Monero, because then, rather than needing to own an ASIC to get money on the cryptocurrency network, all you need is a computer that has enough memory to do that. Okay, so the idea here is to use a scheme in which a miner has to store data in high-speed memory that is randomly accessed in order to generate a solution. Okay, and this evens, I mean, it kind of evens the playing field, but not really. I mean, getting the parallelization in ASICs is much easier than it is to buy a whole bunch of memory resources, is the idea. Okay, the other alternative is to have a puzzle algorithm that continually changes. Then you can't bake in the algorithm into hardware, which is what these ASIC folks are doing. And this is the programmable proof of work that is being proposed in Ethereum. And this is for Ethereum 2.0. Okay, so both of these are used as part of CryptoNote and Monero, which is why a lot of people are trying to hijack laptops in order to mine cryptocurrency. Okay, the last thing I want to talk about is privacy issues on the blockchain. So the blockchain is supporting consensus, correctness, authenticity, and availability, but it doesn't support privacy out of the box, or most blockchains don't. All of these transactions are viewable on the blockchain, and if you can, if the person submitting transactions onto the blockchain doesn't have good operational security, people can view the transactions going to the blockchain and then figure out who is associated with particular addresses. And if they're doing things that are illegal, then law enforcement can go after them. So that's actually a good thing for a lot of people, but there are some people who would rather be anonymous. And right now, the facility for basically remaining anonymous on a blockchain isn't there. And so the issue is that all of these transactions are public. And tracing Bitcoin transactions per wallet is actually simple. Because you have the entire blockchain there, you just build an index, and then you can support querying of that account, and you can see that account's entire transaction history on the blockchain. So this is what law enforcement does in order to go after people who are using Bitcoin for illegal purposes. And then they can try and trace where these requests are coming from and triangulate where the illegal activity is from. Same with Ethereum. All of the smart contract executions are public. You can't execute on private data on Ethereum because everybody needs to have the same state. And so there are some proposed solutions. So one of the solutions that is typically done for getting anonymity is to use this idea of crowds. So strength in numbers. If I can mix my transactions with a whole bunch of other people, then that ambiguates who these transactions are from. And so a crowd is basically a clearinghouse account for mixing all these coin transactions. And the idea is to support what's known as K-anonymity. And K-anonymity means that I am one of K people. Like if I mix my transactions with K-1 other people, then I achieve K-anonymity. You can't attribute a certain transaction to me, but you can't attribute it to the group K. And so then the idea is, can I make K as big as possible, and then it won't be traceable. So this is a picture of what it looks like. I have a bunch of transactions here on the left. I throw it into this blender, and then so these are a bunch of coins. I throw it into a blender, and then I distribute those coins, and then all of a sudden I don't know which one of these three people is the actual person who who had a particular coin. But should this be legal? So here's a question. This is a figure of a Bitcoin laundering scheme where you have dirty Bitcoins, and these are Bitcoins associated, for example, with ransomware campaigns. So you say, hey, if you want your computer back, send a bunch of Bitcoins to this address. But now you got a hot address, right? Like that address is known to house illegal, whoever accesses that wallet is known to be an illegal, or is known to be a criminal. So then we can go after that person. So then the idea of some of these laundering services is to accept Bitcoins from everywhere, and in particular, dirty Bitcoins, and then to mix them all up together in one wallet address, and then to reissue these Bitcoins from this address minus the fees. So obviously you got to make money, so you'll subtract off the fees. So the question then becomes, should this be legal? What do you think? Should law enforcement go after the mixing operation? You say yes? No. That's interesting. Why would you say yes or no?
I guess in my mind, moving the money around isn't in itself an illegal act.
Mm-hmm.
And so I like to have a clear line between illegal versus legal.
Okay.
Even though it is helping criminals, there should be other methods to go about.
So here's a good question. What happened when we did the similar idea for something like BitTorrent and Napster? Why is Napster considered illegal? And why is stuff like, the next one was Morpheus. I don't know if any of you remember. I remember it because I was downloading MP3s at the time. Why was Morpheus or Napster, why was that considered illegal? But BitTorrent, which is, they're using BitTorrent to pirate movies, why was that not considered illegal? Because the same thing is playing out with this, actually. In fact, it's very analogous. What is the U.S. statute? What are the U.S. precedents for this kind of activity? How easy is it to shut down? That's true. That's true, actually, yeah. BitTorrent's harder to shut down, yeah.
But if you're a seed client, though, aren't you liable, and that's like a criminal act? You're allowing distribution from your computer. That, if I remember.
So why would, yeah, so then you would go after the user. If the user is doing the illegal activity, then you would go after the user potentially, yeah. They were assisting criminals, yeah. So part of it is the intent, right?
Yeah, reception of stolen goods is illegal.
Mm-hmm.
It's different. You're receiving stolen goods from an actor.
Yeah. So this is actually, the precedent is it depends on how you market your service. BitTorrent was never marketed as a way to pirate movies. In fact, it was marketed as the opposite. This is a way to get large files, things like Linux distributions very quickly, software distribution, legitimate software distribution. The issue then becomes is the bestmixer.io was actually marketing themselves as a money laundering service. And this is where the intent is used to apply the legality or illegality of this thing. But these are legal precedents that are still being made, right? Like, because this is something this is a European case where the European authorities shut the thing down. But those are statutes that we have to actually decide here in the U.S. whether or not we're going to go after these sorts of money laundering services.
Is it really going to make a difference, though? If we shut everything down in the UK and US, they're just going anywhere else.
Yep, yeah, so, well, they're going to go to other places. But, in law enforcement, if you can get all the illegal activity into one particular thing, if everyone moves to that one particular thing, it's a better target. So in the end, you sort of reduce like all the criminal activities to basically either one network. And we'll talk about some of these alternative privacy coins. That actually sometimes helps law enforcement because then you're like, okay, if 95% of the people using that coin are doing things illegally, then I can just look for people who are downloading that software or connecting up to that network, and then it's really easy to identify targets. So this is another thing that to think about. Okay, so this is the quote from this article. The legality changes when a mixing service advertises itself as a successful method, no, pardon the typo, as a successful method to avoid various anti-money laundering policies via anonymity. So it's definitely how you market it, and that's basically how they apply copyright law in the US. A lot of it is the intent of the service. And I think because Napster and some of the subsequent services were marketing themselves as being able to get free copyrighted MP3s through their network, that's where they were held liable for the activity. Okay, ring signatures or group signatures are a cryptographic mechanism for doing the mixing with cryptography. So it's basically an implementation of a mixer. And the example is, so you can have a scenario where 5 users send their public keys alongside a deposit of 0.1 ETH to a group address. And then this group address will be managed in a way that if you have one of the private keys associated with the deposits, you are allowed to withdraw exactly 0.1 ETH from that group. And so this gives you, in this case, anonymity of 5 anonymity. Okay? So this is what's being proposed as a way of getting anonymity in the sending of these transactions. Okay, this is what it looks like. So at the top is what we have right now. So I have one private key, and then I generate a signature, and then anybody with my public key can verify that I signed this. A ring signature is similar, but it has multiple private keys. And it's got a signature where any one of these 3 can be used to validate that this thing is valid. So you generate this group key from the private key of all of these participants, and then people can use the public key of these associated participants to validate that one of them had created this signature. And this is the way they can basically disintermediate the transaction from the identity of the people who are sending it. Okay. So the size of the ring is basically your K. The level of anonymity that you want will be the size of this ring. Okay. And then senders can verify each other using this the public keys that are associated with this ring. Okay, another thing that's being done is this unlinkable payments via one-time keys. And so this is combined, so this is sender anonymity, and the one-time address is a way of trying to get receiver anonymity. And the idea is, again, this is very similar to Tor. This is how Tor allows people to have anonymity of both the sender and the receiver, is to add a level of indirection to everything that goes on in the network. Whether it's transactions or passing messages to addresses. And so in this scheme, the private key of the sender creates a bunch of things. A send key, which is a sort of a private key for doing the transactions. A view key, and this view key is a key that gets distributed to the recipient so that the recipient can figure out how the payment is going to be done inside the network. And then the address, and this address is going to be a one-time address that's going to be used for the recipient to withdraw the funds from. And so the idea of this scheme is that the sender is going to use the send key to initiate payment, and then gives the recipient the view key to access where the funds will be stored. And then it passes through a ring signature because the sender doesn't want to be known. So you get this K anonymity from the ring signature. And then the transaction is sent to a one-time stealth wallet address so that it doesn't persist for the recipient, or the recipient can use that without actually identifying his or her own wallet address. So basically, it's an access to this stealth wallet, and then for subsequent transactions, you can use that as the sending wallet. And then you don't have a trace between the sender and the receiver of this transaction happening. So that's the idea. Okay, and this is all done covert. You can think of this as Tor, is effectively what's going on. Okay, so the example of both of these things being used is ZeroCoin. So this is ZeroCoin is an extension to Bitcoin. And the idea is to do the unlinking of transactions to their origins, to add ring signatures in order to get the anonymity that you wanted on top of Bitcoin. Okay. Let's see. And then the last one is Zcash. One of the things with ZeroCoin is that it hides the origin with the ring signature, but some of these, the destination addresses are still visible. Zerocash tries to hide everything. And this is something that if you are interested, it's basically done using this cryptographic magic called a zero knowledge proof, where you can prove something, two people can prove something to each other without actually revealing what they know. And so this is something that I'm not going to cover in class because this is sort of an advanced topic, but I have extra slides that follow this where you can start to learn about zero knowledge proofs as a way of doing a transaction of proving someone has a particular amount of money without actually revealing the amount of money that they have. So that's something I'll skip actually. Okay, so with that, that's toward the end of the advanced topics. I'm just gonna let you work on your Manticore and then try and help you out and debug for the rest of the class. All right. Yes, I will export them